go. All right. So for containing C, and here we go. Here's the thing is, how do we find those A sub n's? Okay, and well, remember how we found the coefficients for the Taylor polynomial, right? We found the nth derivative at C and divided by n factorial. And so that's how we get a Taylor series for our function f of x. Now, then f of x equals, well, f at C, then f prime at C, what's f prime, times x minus C, f double prime at C times x minus C squared over 2 factorial, and so on and so forth, right? Oops. And it just continues on and on and on. Until you get that nth derivative at C over n factorial, x minus C to the n. But then it keeps going. It's an infinite series. Okay. And when we go all the way to infinity, then our series matches up with our original function perfectly. And that is our Taylor series for f of x centered at C. Now, of course, you already know that a Maclaurin series C is 0. So we just center it at 0, and you get what we call a Maclaurin series. Okay? Easy peasy. Now, we'll develop a couple of them here as we go through. And then we'll have some guidelines that we'll be looking at here for how do we create a Taylor and or Maclaurin series. And then we'll finish up with a table that we have that have some really common series in them, because we can create Taylor and Maclaurin series from the basic ones a lot of the time through some sort of multiplication, division, power within a power, something like that. So let's start with a nice example here. It's example 1, and it's really, it's just about finding a Maclaurin series for sine of x. So find the Maclaurin series for f of x equaling sine of x. Well, obviously, we know what that looks like, right? We know it's going to be the sum from 0 to infinity, nth derivative at the center, which is 0, over n factorial times x minus 0 to the n. And so when you start figuring out what does that series actually look like, well, the 0th derivative, that's just going to be f of 0, right? And then you're going to get f prime at 0 times x, and then you're going to get f double prime at 0 times x squared over 2 factorial, then f triple prime at 0 over 3 factorial, x cubed, and so on and so forth. And so what we'll do is we'll just write out the first few derivatives and just sort of go through here. Well, you know, f of 0, that's sine of 0. Well, that's of course 0. Now f prime of 0, well, that's cosine of 0. And we know that's 1. F double prime of 0 is negative sine of 0, which of course 0. And f triple prime of 0 is of course negative cosine of 0, which is negative 1. And so if I just write down the first few terms of our series then, well, the first term is 0. So the first real non-zero term is x. The next term is going to be 0. Oh. And then the next non-zero term is going to be negative 1 over 3 factorial x cubed. And then of course, you know, you can see what happens. The even derivatives all end up with a sign in them. So the next one would be 0. And then that would be the fourth derivative. The fifth derivative then is back to cosine. So that's a positive 1 over 5 factorial x to the fifth. And this is going to continue on like so until we get, you know, basically what we saw before. We've got x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, so on and so forth. So if we wanted to write this down as some kind of series notation, right? Well, you can see that we have, let's see, if we start at 0 and go to infinity, you know, what's going on here? I've got an alternating series, so I know I've got a negative 1 to the nth power in here. I've got odd numbers as the exponents for x, so I know I've got x to the 2n plus 1 as my exponent, and I've got the same odd numbers as the denominators, but as factorialized. So let's just say 2n plus 1 factorial. And there it is. That's the Maclaurin series for sine. Okay, and I think you can see, like, if we did a quick ratio test with that it would be convergent. You know, if we said, okay, well, let's use that ratio test. Let's do that here. Okay, so what's the limit as n approaches infinity? Okay, so the n plus 1th term. So we've got x to the 2 n plus 1 plus 1 over 2 n plus 1 plus 1 factorial times 2n plus 1 factorial over x to the 2n plus 1. And we'll just do a quick little bit of algebra here. This is, of course, 2n plus 3 for our exponent here. This is also 2n plus 3 factorial, which, you know, remember that there's some reducing we can do here because of the way factorial works, right? We're just going to get x squared over 2n plus 3, 2n plus 2, and then the 2n plus 1 factorial on down would cancel out. And notice that that's going to be 0. No matter what choice I have for x, that's going to be 0, which is clearly less than 1, which means, obviously, we have convergence for all x. We have an infinitely large radius of convergence. Okay, so nice, good function, good power series. Here's the tricky thing, though. What we haven't proved, and this is subtle, but it's important. We have not proved what the series converges to. We've proved that it is convergent, okay, and we and we prove that is convergent for all. Okay, but what we haven't proved, what we haven't shown, is that this series actually converges to sine. The series converges to the actual function f of x that we wanted from the beginning, and that's a subtle difference there, because it seems like, well, yeah, we built it out of the functions, so it's fine, except that there might be other functions that have the same convergence behavior near the zero, or near the center, but maybe that need to be explored a little bit more in depth. And so what we're going to do here is we have to show, okay, so how do we prove that it converges, and it converges to the function we want it to converge to? Okay, and that's what theorem 8.23 is all about. It's about taking care of the fact, okay, yes, it converges, great, fantastic. Yes, it's clearly the ratio test shows convergence, but what is it actually converging to? And so the way we do that, and that's what theorem 8.23 is all about. Okay, it's about proving convergence to the function we actually wanted to converge to. And it says this, it says if, okay, the limit as n goes to infinity, so as the number of terms in the series increases, for r sub n is 0, then in the interval, then the Taylor series converges. And is equal to f of x. In other words, f of x is truly equal to the sum from 0 to infinity of our nth derivative at c. And so that's the trick. Is establishing not only convergence, but convergence to the function that we want it to converge to. If we go back to the sine function, your book actually has a nice alternative here. It says, well, consider this function. It's a piecewise function. And if I were to center this, a Taylor or a Maclaurin polynomial for this function at 0, okay, it would have the same exact polynomial as we found earlier. Okay, if we go back up here to this polynomial, okay, they would both have this as our series representation. Okay, but which one actually converges to the function that we want and which one does not? Okay, so because we can show they both converge because it's the same. Okay, but this function here, this one has kind of a strange look to it. If I sketch it really quickly, basically it does this. It's got a positive one here, it's got a negative one here, and from pi over 2 to pi over 2, it does something like this. And so, how do they both converge to the original functions? They can't, right? Only one of them is the real function. Okay, and so we have to establish through the remainder term, okay, prove that remainder term goes to 0. So let's think about that for a minute. Remember back to Taylor's theorem earlier, we learned that the remainder theorem, the remainder of any, function or polynomial, in this case now series, we said, okay, look, we know that the remainder is going to be equal to a certain, the n+1 derivative at z, okay, sorry, absolute value. The n+1 derivative at a z over n+1 factorial times x to the n+1. Okay. So all we have to do is to take a look at that and say, well, for sine, right? In the case of sine, for sine of x, the n+1 derivative at z is always less than or equal to 1. And so you might remember we substituted in there that Lagrange error formula that said that the max of that n+1 derivative. Well, look, the max in this case is just 1. So we can show that that is then, oops. There we go. Less than or equal to x to the n+1 over n+1 factorial. And if you go way back to section 8.1, we talked in there a little bit about the difference in terms of the rate of growth for exponential versus a factorial. And yeah, the factorial grows bigger much faster. And so we can show that, oh, okay, so if this is the remainder, then the limit as n approaches infinity of x to the n+1 over n+1 factorial is in fact 0. And if you want to, if you're wondering, like, well, okay, what about other values of x? Imagine like a squeeze theorem kind of thing. You can always, pick a value of x and then squeeze it once you have a constant for x. And that n+1 factorial in denominator is always going to grow faster than that exponential. Eventually, I mean, obviously, if x is really big, it'd take a while, but n+1 factorial will always grow faster than an exponential. And that was something we talked about way back in section 8.1. So when we look at this as a sine function, now you see, oh, okay, so we do have convergence to our actual sine wave as n goes to infinity. And if you have the book at the bottom of page 635, they actually have a pretty cool looking little graphic there that shows you different Maclaurin polynomials that come from this Maclaurin series. As you increase the degree, how it does match up quite nicely with the sine. They go up to the 7th Maclaurin polynomial, and you can see it matches pretty well, that waveform. Obviously, P9 and P11 and so on would be even closer, because as we can see here, the remainder does go to 0 as n gets infinitely large. So that brings us to the guidelines. So for us, for when we want to find a Taylor series, okay, there's some nice guidelines here at the top of 636. So the guidelines on 636. Okay. For one, okay, you start finding derivatives. So I think that several times. Okay, and evaluate those derivatives. at the center point. In other words, you're going to find f of c and f prime at c and f double prime and f triple prime and so on and so forth. Okay, and then hopefully, okay, you try to recognize the pattern. Okay, and then you use the sequence to form the coefficients. Okay, we want a sub n to be that nth derivative over n factorial. Nth derivative, sorry, at c. There we go. Okay. And then here's the thing. Once we have that, you need to determine the interval of convergence. Okay, so find the radius of convergence, see what's going on at the endpoints. Okay, figure out what is that interval of convergence, and then now the third thing is, of course, determine whether or not the series converges to f of x. Within its interval. Yeah, we don't much care what happens outside the interval of convergence. But so and we've gone through these steps now with the sine function. But yeah, so that's the basic idea every single time now. When you get the question, write the Taylor or Maclaurin series. It's going to kind of, okay, so there's these three steps that I need to do. Take all my derivatives, not all, that would be infinitely many. Take a bunch of derivatives, evaluate those derivatives at C, look at the pattern that emerges, okay, and then use that to come up with that series, okay, and then determine the interval of convergence. Now, usually that interval of convergence, right, when we're doing this stuff, is going to come from the ratio test. Okay, it's not like power series when we wrote them before where we were using geometrics. You might get lucky. You might get lucky and see one that's a geometric, and then by all means use the geometric stuff. But these are, generally speaking, going to be a little more complex, a little more complicated, and so we don't have, or we won't be using the sort of simpler version of the common ratio as we lesson one. We'll be looking at the actual ratio test and determining, what does that mean for our radius of convergence, and then checking the endpoints to see if we have convergence to the endpoints. And then finally, examining the rate, or the remainder that we have, that Lagrange remainder term, and put them all together. That's how you prove you have a nice Taylor or Maclaurin series. To help you, on page 638, there's a table here of some common or the elementary power series, because we can combine power series together and do that kind of stuff with them. Let's see here. I can show them to you here. I think. Oh. Unveil that. There we go. So there they are. And again, this is page 638 in the book. And you can see that we have a few of the ones we've already worked with. 1 over x plus 1, natural log of x, e to the x, sine of x, cosine of x. They actually gave you a nice one for arctan and arcsine as well. And at the very bottom there, they actually give you one for a binomial. If you just have the binomial 1 plus x to the k power, you can actually write a very nice Maclaurin or Taylor polynomial for that as well. And there it is. And hopefully these will help you as you go to build some other series. For example, I won't work this one out for you. But they said, look, let's take a look here at cosine, but instead of cosine of x, we're going to do cosine of the square root of x. Now, I don't want to do a bunch of derivatives for cosine of square root of x, right? Those are going to be messy because the chain rule is going to be involved in that. Well, the good news is we don't have to do that because we know that that's cosine of x to the 1/2, and using the theorems from 8.8, you could just plug in x to the 1/2 into your series for cosine of x, and then you could come up with that series there, 1 minus x over 2 factorial plus x squared over 4 factorial instead of getting the other powers. And it works quite nicely. So that's the, so put this back into our notes here. So that's the idea, is that we can use those elementary power series to come up with a much easier way to build the power series for our functions. So, all right, let's see here. I'm going to shut off our recording so that we can ask questions here. Find the recording button. Hold on a second.